Let me ask you guys this. How do you guys study? Do you think, now homework obviously is a part of studying for a class like this, but my God, please, dear God, if you're doing it, do all the homework. That's going to help you. If that's the only thing you are doing, you might not be getting yourself ready enough for a test. Obviously, I am a pure geek, but what I would do is I would write the ideas from every section and make sure I understood the ideas, right? I would get to the point where if you told me an idea, I could tell you what section it was in, if not what page it was on in the freaking book. And then I knew I was ready. Right? I was not born with a photographic memory. So if I get it to that point, I'm like, it's in my freaking head. So, for example, if you look back at section 13.3, I would write down the arc length formulas, right? What other ideas do we have in here? The arc length function. This is where the curvature is. So I put the curvature function and then next to it maybe what it really tells you, right? Because I might ask you a conceptual question. You know I probably will. Let me see. Osculating plane and stuff like that. The normal plane. I like it. 13.4, I'm going to give you, I'm not going to give you the basic idea, which is, there's one thing I want to make sure you guys understand about this too. I'm going to give you something like this. I'm going to give you the acceleration broken down into its components. I want to make sure you guys understand there's a difference between this and this. And the book is easier because they got the bold thing working for them. But if you look at this formula, this little v here is not bolded. So it's not the vector function. It's actually the length. So this is the length of r prime. That is the speed, exactly, in the direction of motion. So I'm always curious if anybody wonders about this, because is everybody cool? We actually kind of looked at this function. We derived it a bit. We talked about what it means. Yes, sir? Yes?
I was wondering, I was getting confused by what speed prime meant.
So that is the change in the velocity in the direction I'm moving.
So
Let me make sure that sinks in. That's the change in my rate of change of my position, how quickly that's changing in the direction that I'm moving.
Why don't we just call that A?
Because A is a much more general idea.
If that was a circle, then that would be 0.
Exactly. So the true full acceleration is due to how quickly I'm changing my velocity in the direction I'm moving, but also possibly something pulling me in. If I'm on a banked curve, for example, or if I am attached to the end of a string or something, I've got something pulling me in, some centripetal acceleration that's pulling me in. That would be this guy. The acceleration is acting along the normal direction.
So we would have to find the tangent vector, the velocity vector, the curvature, the normal vector, and the speed for this question.
Yes, that's all. I like it. So, but I'm probably going to give you an R of t. I'm going to ask you, basically, to find all those things, right? Right? And then I'm going to give you this and say, just put this together. Tell me what the tangential piece is and what it means. So let me give you an example. Let's say R of t was 2 sine t cosine t. Sure, just to change things up a little bit. Let's go in 2 dimensions. So what's R prime?
2 cosine t.
All right, everybody's with me so far, right? All right. Now, what's the length of this?
4 cos t squared plus sine t squared.
Yeah, square root of
Yeah, square root.
4 cosine squared t
Plus
What's sine squared t? All right. So I could do a derivative of this, right? That would be v prime if I do a derivative of this. Now, I really want this to sink in. Now, if I do a derivative of this guy, I'm going to get the acceleration. So if I do r double prime of t, I'm going to get the acceleration. And what's that going to be?
-2 sine t.
Yeah, negative 2 sine t.
Negative cosine t.
Negative cosine. I like it. But if I take a derivative, now if I take a derivative of this, am I going to get something related to that? Not directly, no. So there's the order that you take a length and do a derivative in matters, and that's really what this is all about. That is purely the acceleration in the tangential direction, in the direction that I'm moving. But the total acceleration, why would I be turning? Because some other thing, some reason I'm accelerating towards the center or some other direction.
So for the KD squared, is that just the magnitude of r prime of t squared? So you just take away the square root of v?
Yeah, this is going to be my, this is my v.
I get that. And then you take
And then v prime would be the derivative of this. You with me? I like it. I like it. I like it. It's a really small detail about length and derivative. The order you do those in matters.
Are we going to get the formulas where they gave us like all these like r double prime, cross primes?
You're talking about the kappa and the TNB stuff? Or-
well, not that. It was where was it?
like what you gave first for the equation.
Yeah, like a sub t is equal to r times general.
Oh yeah, I'd give you those.
Okay.
Again, there's no value in memorizing those formulas for me, for this class. Because again, what matters in this class is that is a specific application of using something you need to know from this class. So the more specific applications we actually use these on, the more we can make sense of them. So my big thing for this is going to be, I'm going to make you do it. I'm going to give you the equation to use, and I'm going to ask you what the hell does that mean. So that would be a good thing to be able to figure out.
So this is just uniform circular motion, right? That's what that sounds like.
No, this is more general than that. But you can. There was a problem in the homework that said, what if your velocity was constant? I can't remember which one that was. There was two parts to it. Oh, I can't remember which one. No, that's not. Maybe that's the one I'm thinking about. The acceleration and velocity vectors are orthogonal. There was that one.
I think it's 36.
36. Yes, beautiful. If it moves along a straight line, what would happen to this vector? If it goes in a curve without changing its speed, what would happen to this? So if the speed isn't changing, then obviously this is 0. So it's completely dependent. That would be what exactly. So that's part B of that problem, though. The first problem says, what if you're traveling in a straight line? Then this is going to be 0. This piece, the curvature is going to be 0. So this piece is 0. So it's going to be completely dependent on just how much you're changing your velocity in that direction. I like it. So that really that problem explains what each of those pieces are and what they're related to. Okay. So anytime I turn in a curve, there is some force that's making me move in that direction. That's actually making my velocity change. How many guys? If I put this up here, does this look familiar to anybody? If you put an electric charge into an electric field and a magnetic field, the force it experiences is equal to this. Now you can break this down into how it moves. The magnetic field, who's taking physics? Can the magnetic field change the velocity of a particle? The speed of a particle, let me say it like that. The speed of a particle. No. it works at normal directions to it. So if you have a particle coming into a magnetic field, it's going to start to go in a circle. The circle's direction depends on which way the magnetic field is pointing. Does this sound at all familiar for you guys?
Well, we're in history right now, but we haven't gotten to it yet.
Oh, okay. Oh, cool. But there's a lot of similarities here between those two. Oh, the QE part, okay. You don't have the magnetic field. Okay, I got you. That's where things get really, really neat. That's why things curve, is because the magnetic field applies an acceleration depending on which way it's pointing that makes it turn. So that would be that normal component of the acceleration. All right, cool. So when you get there, you're like, oh shit, I've seen this stuff. All right, for the rest of us, if anybody out there that's never taken physics, don't worry. You don't have to have taken physics to understand this.
You're gonna have to know how to use the squeeze theorem thing if you give us that.
Well, I don't think I actually ended up giving a problem like that in homework, did I? I don't think I managed to assign. On WebAssign there was?
Yeah, there was one problem.
All right.
Talked about squeeze on that.
So the thing about WebAssign very quickly is they have a subset of the problems in every section that's available for me to assign. So I just try to assign something near that problem that's the same idea as that problem. And at first I didn't realize I didn't assign anything that had a squeeze theorem in it. But so since I didn't do it for the textbook, I'm not going to have it on the test. The application of squeeze theorem. The important thing is to realize there are things like squeeze theorem that are out there that you can use as a rigorous proof of a theorem. There's also the epsilon delta stuff that a lot of you guys unfortunately had these wimpy teachers that skipped it. Yes, I just said that. Yes. That's what I'm saying. If your teacher didn't skip it, they're good. They got their calculus muscles up and going. Some of them are wimpy and they skipped it. They're getting me some shit about that. There was one last thing that I had to say.
Do you have any teachers that come to you after watching one of your YouTube videos? It's like, I know you're
No, not really.
That's
You guys can go tell him. He watches a video from the state. And, I think he's talking about you. It's like, bring it. Bring it. Sometimes I'm worried if my dean will watch, depending on what happened that day.
Oh, yeah. There was one homework question where we had a table of values for a change rule.
Oh yeah.
15. Somehow, like I checked in the solutions manual to make sure I did it right. They told us to check at G of U at 0, 0 and G of U at 0, 0, but it switched to 1, 2. Like
good. Yes.
Problem, and I was really confused about why no.
No. So, okay. I like this question a lot. It's related to Calc 1 kind of questions we got when we first learned derivatives. So they give me this here, these values, 0, 0, 1, 2.
Which one is this?
15 and 14.5. So they tell me what does that mean, for example?
It means at 1 and 2 when f of x is held constant. Partial.
When y is held constant at the point. If I'm at the point 1, 2, if I hold y constant,
That's right. That's 2.
if I move in the positive x direction, the output will move up by 2 for every step. At that instant, this is what it looks like it's going to do. So that should sound very much like original derivative talk, because that's exactly what the hell this is. It's just that now, instead of being in a plane, the xy plane, and I really only have one way to look, now we've opened it up. And now I've got to say, I can't just say as x change. Now I've got to say in this direction. Right? So we're going to make that even more general when we get to 14.6, but we're not there yet, so let's not worry about it. All right. So they give me all these values, and they give me this function. Yes, okay. Oh, okay. So now, so this is a function that uses f. Now here's what g is doing. And inputs based on u and v. So let's see what happens here. They want me to figure out gu at 0, 0. Let's just do this by itself. And I'll let you guys do the other one. So in order to figure this out, I obviously have to figure out what the hell gu is. Let's go this way. So I want to figure out what GU is. And what does GU mean? Well, let's replace that with more specific language here, more specific symbols. What does G sub U mean? G. Partial. Of G with respect to
U.
U. Good. Now how do I calculate that? What's G composed of? It's composed of F. So it'll be, what starts me off?
Let's call that partial x. I mean partial g and partial.
Partial of F with respect to,
Let's call that
Plus sine v.
yeah, we can just call this,
x. Partial of x.
yeah, so this would be like Fx. Cool. Times, well actually, you gotta,
Partial x
Times partial with respect to u.
yeah, partial of, let's just go ahead and write it all. Partial with respect to x, partial of x with respect to u, actually it should be the other way around, right? Do they tell us what u and g? No, they don't. Wait. Oh yeah, okay.
Is it starts with u?
Yeah, partial of f with respect to u, partial of u with respect to x. Okay, I got you. Plus,
Partial f. Respect to v.
oh, do we need a plus? So I just want dg du right now, right? Cool, I like it. So df du du dx plus, do we need to plus anything?
Partial of partial v.
Yeah, partial of f, partial of v, but that's going to be for the next one. All right, let's start the next one off. What's g of v going to look like? Partial of g with respect to v.
Partial f.
Partial of
Partial v. Partial v. Partial v.
what?
Oh, sorry, not u, v.
So are we just calling u plus sine v? Are we just calling that whole thing u?
Yeah.
Or
Because if
because
No.
g is a function of u and v, so is that
So this is like my x here, right? And this is my y. X equals this. So maybe it'll help out if we do this. If we take what they sell us, g of u, v, so actually help me out. It's f of x, y. I mean, f is a function of x and y, correct? But x is e to the u plus sine v, and y is e to the u plus cosine v.
So for GV, should it be dV over the partial to y, not x?
Exactly, good. So this part here, so if you write it like this, you can see f is a function of these. So I have to have partial of f with respect to x, partial of x with respect to u, because x is a function of u. I like it. So f is a function of x and y. So what else do I have to have here? I have to have the partial of f with respect to, what else? So f is a function of what? X and y. I love it. Right? You guys with me? So whenever I do any partials, I have to have partial f with respect to x for sure, and partial f with respect to y for sure. It's a function of two variables. So this will be df dx dx du, df dy, dy du. Y is a function of u and v. Okay.
so
Now let's take this one by itself. So at the point, was it 0, 0, right? That's the question. What's GU at 0, 0? So do I know what fx is at 0, 0?
It's 4.
It's 4. But this is a function of u and v, right? So let's be careful. Oh, here, that's your question. Okay, now I got you. All right.
Why do we move to the 1, 2 column?
So you ready? So the question is, what is GU at 0, 0? So it's telling me that u is 0 and v is 0. So then what's x?
1.
Yeah, 1.
Oh,
And what's y?
2.
2. I like it. So you got to step through the fact that g is a function of u and v. So when they say, what's GU 0, 0, what are they saying is 0? They're saying that u is 0 and v is 0.
So instead of doing like having G, U, V, F, all that other stuff, why didn't they just call G, Z, and then say it's equal to f of x, with x being a function of u and v and y being a function of u and v?
So there's a lot of different ways to do this problem. There are actually a lot of different ways to look at this problem, but the fact that we don't know what these functions are, and they gave me information that's dependent on x and y, right? They kind of told me to have to break it down like this. I mean, if I knew what the functions were, I could do it differently. So yeah, you could call this z.
Yeah. It just seems so weird. Like, I was able to do this problem, but I'm just not really sure how this works. Because we have...
I think if they would have given it to us like this, which is the way a lot of the other problems are given to us, right? They have a function of x and y, where x is some function of, in this case, u and v, but like earlier, s and t. Those kind of problems, there's a few problems that look just like that. Then it would have been a little more obvious, but they plugged that in there and made it a little bit freakier. But since I have information about fx, I have to take a derivative with respect to x. That much is known. And then I realize, oh, my x is a function of u and v. And that's why it turned into 1, 2 now. So this will be, so when you do this, GU of 0, 0 means that my xy is actually 1, 2. Because when u is 0 and v is 0, x and y are 1, 2.
So if you have G as u, and you want to take partial G with respect to u, then why do we only take one part instead of both, since the entire G of u function is equal to both x and y, not just x? Why are we able to, because we don't know what it's a function of, so why are we able to just say y goes away? Like, does that make any sense?
As is your new
Yeah.
So what we are used to, what we're really more used to, is having like this here, and then doing dz dt, right? What would dz dt look like for this? In fact, let me just make it like this.
Well, it would just be partial c, partial x,
I like it.
dx dt, plus partial c, partial x, dy.
So now, what if I were to say, all right, actually x is a function of u and v, and y is a function of u and v. Then I could say dz du equals something, right? And what would that look like? Dz du would be dz dx dx
Yeah.
du, dz dy dy du, and isn't that exactly what we
That's what I'm wondering about, like when we get G as a partial just V, why don't we get two parts? We only get one part. Does that make sense?
So they could have given this problem like this. They could have said z is a function of x and y, where x equals this and y equals this. Find, yeah, they could have said find zu at 0, 0, right? But then it would have been harder to tell people that this 0, 0 refers to u and v, which is what z is really a function of. So the reason they had to say it like this It's because they want you to understand these inputs are for u and v, not for x and y.
But even then, when you took the partial du, you would still get partial z, partial x, partial u. Why?
The only thing that would change is you might think that this is supposed to be for x and y. And in this problem, they want you to realize it's supposed to be for u and v, not... So this 0, 0 is not going to be plugged in for x and y.
Yeah.
That's the only thing that they wanted to make clear. That's why they wrote it like this. If they would have just put a z here, I would have assumed my inputs would have been x and y, maybe.
But why does partial g of v, why does that only equal partial f, partial
Oh, we haven't finished rewriting this. We had a first stab at it, and we stepped back to see why that didn't make any sense. So now we see that this should be what?
Oh, okay. That makes a lot more sense. I was really
Yeah.
confused by
I mean, we wrote down just to see what would happen between the two of them and see if it made sense. So this didn't make sense. Now it does. df dx, because f is a function of x.
Yeah.
And then dx dv, because x is a function of u and v.
And then
Plus, yeah.
okay. I was really confused by that. Partial thing.
So I do end up with df dv and df dv, just the two components together making the complete. And you could put g there if you want to, right? Because that's really what that is. Do you see what I'm saying? Okay. Same thing with dz being replaced with df, the same idea. dg is really df, because they are equal to each other. All right. So that problem, they wanted very specific understanding of what was happening, but they could have written it in a lot of different ways, definitely. Cool. And now you just plug and chug what you know from here. I like it. So if you really want to see how to write this so it's really in your face, this would be fx of x evaluated at 0, 0, y evaluated at 0, 0, because what is x? It's a function of u and v. Shit, so when you plug that in, that's where you get the 1, and that's where you get the 2. I like it. Let's see if I can...
For your questions on the test, is there going to be anything particularly difficult that we should review?
I mean, to me, probably the weirdest part is this chain rule stuff. Tangent planes, linear approximations, the same thing. I mean, that's the kind of thing you want to write for yourself. So if I say find the linear approximation to this surface at this point, you just say to yourself, find the tangent plane. And then I can do whatever the hell he wants me to do. It's not a separate process. I always hated that they made it sound like a whole different process. I don't know, let's see. I think most everybody understands the limit stuff, the path stuff. I mean, we didn't get too deep into that, but just the understanding of why you have to take into account different paths now, and you didn't have to before. We sort of did. The only two paths we had to take into account were from below and from above. But now it could be from this angle, from that angle, along this curve, along that curve. Oh my God, every possible approach. Yeah. It all depends on what makes the least sense to you. Some of you guys are like, I can narrow it down to 13.3 to 14.5, Jeff. Damn. Oh, the implicit differentiation rewrite using partial derivatives is an interesting thing to realize exists. I'm not going to make you memorize it. But like I said, the chain rule, they have the general chain rule on page 980. And just, I'm pretty sure, I did assign a few problems in 14.4 that actually gave you points to approximate.
Are you talking about pulling from the chart?
No. Like number 20. I might not have assigned number 20, but I'm pretty sure I assigned at least one thing there. So find the linear approximation and then use it to estimate at this point. Okay, good. Because that should feel a lot like what we did in Calc 1. It's the same exact idea. Yeah, I don't know what else to tell you because it really depends on what makes more sense, what makes less sense. Let's see.
Oh, are there going to be any problems like 14.4, question 34 with the finding the amount of metal in the tin?
Which one? Question
34.
No. The reason I put that in the homework is just so you can see a nice specific example of